Ever appreciated the huge repeating framework of a building under construction? Now imagine that on an atomic scale and you've got a metal organic framework. Metal organic frameworks, or MOFs, have a pretty self-explanatory name. They're enormous ordered lattices of metal ions or clusters of metal ions linked together by organic molecules. Organic molecules are basically any molecule primarily composed of carbon. These lattices of metal ions and organic molecules can repeat in 1, 2, or 3 dimensions. What's neat about MOFs is that they are very porous, like extremely porous. MOFs can have porosities up to 10,000 meters squared per gram, which, to put that into perspective, means that 1 gram of that kind of MOF's internal surface area is equal to about 1 city block in Manhattan. Wow, that's pretty big! So because of that, MOFs have a much larger surface area for the volume they occupy than traditionally porous materials such as zeolites, which in turn makes MOFs nifty for, say, storing things like gases in their pores. Gases love to spread out and occupy as much space as they can, but when stored in MOFs, they're forced to be more compact. With such high porosity and surface area, it's easy for MOFs to carry much more gas for its volume than its current counterparts, which also makes MOFs an efficient potential alternative for storing, say, hydrogen fuel or methane gas. A natural gas-powered bus then wouldn't have to stop as much to refill its tank if it had a MOF fuel tank. What's more, you can tune the sizes of MOF pores, which makes them quite flexible catalysts. Their large surface areas also make it easy for many reactant molecules to attach to them at once, speeding up the rate of a reaction, which is the mark of a good catalyst. So how are MOFs made? Well, MOFs are typically grown as crystals in solution. If you made rock candy in grade school, well, it's a pretty similar idea, at least in most cases. Typically, you'd put the metal ion and the organic linker you want to work with in a solvent, and by varying the conditions, such as temperature, pressure, pH, type of solvent, time in oven, you get a different MOF with a different property. In that sense, making MOFs is kind of like going to Build-A-Bear. Now, in 2012, scientists from Kyoto University developed a way to make MOFs into thin films as well, like a coating. They put MOF flakes into an organic solvent and drip the suspension onto water in a beaker. Since organic solvents don't mix well with water, the suspension spreads out over the surface of the water and the MOF flakes get carried along with it into a thin sort of film. Researchers then took out the film using a rubber stamp, which is pretty cool. Okay, so why should we care? Well, MOFs have enormous potential to change every bit of our lives. Taking advantage of just their porosity and internal surface area, scientists have so far experimented with using MOFs for drug delivery, water purification, and even catalysts for reducing CO2. So stay tuned because MOFs will be popping up all around you.